I've been a developer for nearly 25 years and having fun with Scala for about 10 years. I work as a software backend staff engineer at Ledger in Paris. Uh, I present Ledger a bit. So it's the world leader in cryptocurrency security, but not only. We are securing all digital assets. We built an hardware wallet storing your private keys, and to be able to have a fluid user experience, we develop a bunch of services to use this wallet. And I'm developing backend services for this, and more specifically, whole backends that communicates to the blockchains. So we're about 650 employees in 9 locations: France, UK, US, Singapore, Switzerland. I think I don't miss any, mainly in research and development. So we're about 20 Scala devs, and our main service we develop under about 30K requests per second in average, let's say. And we have a lot of open positions, so you can always see us. So let me tell you a story. In a not so imaginary code base, we found this class definition. So it describes a bank account and an IBAN. So it's a French IBAN. Sorry, having 6 fields as string. So everything looks good until we found this. If you don't see the difference between the two codes, it's the parameters are scrambled. So we try this, and the code still compile and fails at runtime. And the code before also compiled and failed at runtime. So we can do better. We're using Scala, so we should be able to do better. So first, maybe with type aliases. So here we create type aliases for each field. So the code is more readable, but there's no validation on the fields, and substitution are always possible. So we try with value classes. Classically, we defined our value classes for each field. So here it looks good, and we can't scramble the parameters as it won't compile, but this one still compiled, and we have invalid values, so it still fails at runtime. So we'll have some validation. Here we're having basic validation. It could be way better, but here it's simple for this talk. And when an invalid value classes, an exception is raised. So in production, it will fail, and we don't want this. So we'll validate without crashing, and we handle correctly invalid values. So first, we define our own error type, so which has only a message. And then we define smart constructors for each value class. So here, the definition of the smart constructor that returns an header so we can handle the error. And here the logic of the validation. We could have used other type classes such as validated or validation, depending on what you're using. So we have to do this for all six fields. So it's quite long to write, and as it's written by hand, errors can be done. Here, let's say if we mix these two types, the number of character may be wrong. Another thing, as we're using Scala 3, why not using opaque types? So here's the code for a single type. Here we have a zero cost abstraction for our validated data type, but it's really cool because we can use it easily, but it's very, very verbose. So here I showed you all the techniques that are used classically, and in this table we can see how each strategy behaves in terms of legibility, the strict order parameter, validation, referential transparency, performance, conciseness, and compile time checking. As you can see, there's no technique that responds to all what we want. So let's try something. There should be something smarter, shorter. So let me present you iron. What is iron? So it's a composable type constraint library that enable constraints binding to a specific type at compile time. It's written using Scala 3 features such as macros, inlines, extension method, and union and intersection types by Raphael Lamaitre. So what is a constraint library? So how do we define a constraint? First, it's just an empty class. And then you define how the constraint behaves. Here, we want to define the positive integer constraint. So we are defining how we test the value that is given and what is the message if the validation isn't good. It's at type level. So when we define a value, we can, by using the column pipe operator, we're refining the hint type with the positive constraint we just declared. And here, if we give an invalid values, it would lead to a compilation error. And we can compose constraint easily by using type intersection. Um, and again, here, invalid values lead to compilation error. And the message here is different depending on the constraint that has been violated. First, here the error should be strictly positive, and then it should be less than 42. So how does the validation behave? Here we have just a simple code. The difference between this one and the previous is just that the value is not defined on the same line. But when we compile, we have this compilation error saying we cannot refine values because the predicate can't be evaluated. If we see here, so the problem comes from the fact the compiler doesn't know what is the value at compile time. But we have ways to fix it. In fact, we have two ways to fix it. Either we inline the value, so at compile time, in the second line, the compiler will know that the value will be 42, or we can use the refine unsafe extension method, and it will give directly the refine type. And if an invalid value is used, we have an illegal argument exception because we use refined unsaved. So if we don't want to throw an exception but handle invalid values, especially if the value is not known at compile time but at runtime, that is the vast majority of the case, we can use iron in a functional way. So here we are having a for comprehension to parse all values and yield an either if with the validation result for all fields of the IBAN. The problem here is that the implementation on the constraints leaks everywhere this type is used. So what can we do with this? We can, thanks to Scala 3 opaque types, we can hide the implementation. So we're defining the opaque type as a sub. Here we define it as a subclass of int to be able to use the refine type the same way as an int. And then for easier usage, we make the companion object extends refine type ops that it is defined in iron that provides utility method. So this utility method are refined methods, so either with options and so on to have to have access to the refinements. We can also factorize the constraint. Here, it's a piece of code that we're using in at Ledger. It's the definition of the Satoshi type, which so Satoshi is 100 million. So there's 100 million Satoshi in a Bitcoin, and there can be only 21 million Bitcoins ever. So we put this in the type system, saying the constraint is positive because it's a money amount, so it's always positive, and less or equals to 21 million times 100 million. We are defining our type and the companion object. So after, when we're using it from an long value, we're using sats.either or sats.option, depending on the case. So if I sum up, if I add iron to the previous table we saw, here we have at least something that fulfill all our requirements. So I won't repeat it, but here we have a concise solution and compile type checking. When we rarely write vanilla Scala, but we are using a lot of libraries. Fortunately, Iron loves the Scala ecosystems. It has integration with a lot of libraries. First, for the refinement output, depending on which FX system you're using, it has some refinement method. So validation for the IO, validated, or either plus parallel for type level. But it has also integration for a lot of utility libraries. So Tapier's for endpoint definitions, one of the few JSON library, property-based test, configuration, database access, CLI tools, and so on. So how do we define our model? Here again, it's a type in our code base. It's a tag that has a name and a value. The name should never be empty, and its length must be equal lower than 128. And for the value, it's quite the same thing, but it may be longer until 512 characters. So here in Tapir, we want the latest account addresses. We are defining this endpoint. So we're importing the integration, and after we just using the type of the refined type. For Doobie, when we want to store at the other end of our application, we're using the import given of the integration, and then we're just taking the refined types, and thanks to the implicits given by the sorry by the integration, we can directly here use the values. But what if my preferred library isn't supported by Iron? So it's quite simple. You can write it. So that's what we did for Doobie, because at the time when we started to use Iron, Doobie wasn't integrated with it. So brace yourself. I'm going to show you the whole code of integration for Doobie. Yeah, that's it. 7 lines of formatted code. we just define how to transfer back and forth between the base type and the constraint type using this mirror, and that's all. So if you have to remember something about this talk, first, iron helps a lot with making illegal state unrepresentable. Quoting Yaron Minsky, the famous quote. It helps us a lot to reduce the feedback loop right to compile time. So now we are detecting at compile time bugs were detected before at runtime or even in production. Also, it increased the reliability and legibility of our code. And more importantly, Scala 3 type system is incredibly powerful. So you can use it at its maximum. And if you don't know how, you can start quite easily with on the Scala website docs. It's nice to understand and know this. So thank you. I think we have nearly 5 minutes for the question. Here, scanning the QR code, you'll find all the slides. And you can reach me on Blue Sky, or there's links on my website here.